This is Algebra 2 with Trig, 6.3, Day 1. We're talking about the domains. The domain of a function consists of all x values such that the function is defined. What we're talking about is trying to find out what x values work in a function and to try to rule out the ones that don't work. So when we look at p of x is a parabola, and when we work with a parabola, we can see that all the values of x will always have a spot to land on the line. Even way out to the side, it'll reach up high, but the graph will eventually reach there. So all real numbers that is the domain, and this symbol, the R with the two lines, represents all real numbers. So that's saying that any number you can think of can be plugged into this function. So as you think about other functions, there are two main concerns that we have that are really going to limit what our domain can be. The restrictions that we need to be concerned about is when there's an x value in the denominator, like we could have here with this equation. What we're concerned about is that denominator being 0. The denominator of a fraction cannot be 0. So when we're restricting our domain, we need to include values that would cause this to occur. So to figure this out, we're going to set the denominator to 0. We're going to solve for x. And then our domain is going to be all real numbers except for the value that we find. So in this case, we'll take our 3x plus 4, we'll equal it to 0. We'll subtract the 4 to the other side. Divide by the 3. So x equals negative 4/3. What that means is negative 4/3 plugged in here is going to make this denominator 0. And in this equation, if the denominator is 0, it would be undefined. So we can plug in any x value we want, 1 and 2 and 3, even 0. You can plug in negative 1, negative 2, any number you want, except you can't plug in negative 4/3. So the domain for this expression, or for this equation, is all real numbers except x equals negative 4/3. Another way that we could write this is an interval notation. We can go from, well, for this one, interval notation would be from negative 0, so it can include negative 0, all the way up to negative 4/3, but we can't include that. And we're going to union that with negative 4/3 all the way to positive. So that would be interval notation. It's kind of silly looking in this case for this. This would mean it can include all the numbers here, it can include all the numbers there, just not the numbers negative 4/3 itself. Another situation we have to worry about is if a radicand was to be 0. If we have an even index and the radicand was 0, which it cannot be, we cannot take the square root of a negative number. So the radicand of a root with an even index cannot be negative. Remember that the index is a small number in the corner of the radical. So this means we want non-negative values. So non-negative does not mean just positive. 0 is not included with positive. It's not included with negative. So we want values that are greater than 0 and also include the 0. Those are considered non-negative. So what we're going to do is set our radicand, set what's inside the radical equal to 0. In fact, we're going to set it greater than or equal to 0. It's an inequality. It's a group of numbers, not one specific number, because it's any number that makes this negative. So we're worried about any negative numbers. So what's going to make this greater than or equal to 0? That's what we want. So by adding the 2 to the other side, we want x values that are 2 or bigger. So our domain is going to be x is greater than or equal to 2, or another way to write that in interval notation is to include the 2 and then go bigger than that, which is positive infinity. You can't reach positive infinity, so you got a rounded bracket. You can include it equals 2, so that's why it's a square bracket. This one is greater than or equal to 2. If we would get a domain that was just greater than or equal to 0, the way that our book often phrases that domain is to call it non-negative real numbers. That includes 0 and positive numbers, where just positive only includes numbers bigger than 0. This includes 0 and the bigger numbers. Now, the third scenario we have to worry about is if we have both situations. We can't let the denominator equal 0. So if we were just worried about a denominator, then this would be all real numbers except 0. But we also can't have negatives inside of a radical. So we can't include 0 and we can't include negative numbers. So this case would be x is greater than 0. If we're dealing with a situation where x is greater than 0, another way to phrase that besides our inequality is to say all positive real numbers. Now that doesn't include 0, just the positives, and of course that doesn't include negatives. So this is an overview of domain. So next we're going to work on problems dealing with that domain. On our next page, we're looking at our operations of addition and subtraction. Multiplication or division. These are all operations that we can do with two functions, and then we can discuss what our domain and range are. So the domain of h is our new function that's made after adding two functions together. It consists of x values that are domains of both the f function and the g function. So you first got to start out with those parents. You got to figure out what are the domains of this function and what's the domain of that function before you even consider what's the domain of putting them together. Multiplication, this is where a lot of trouble is going to occur, and also with division. One issue with division also is that the denominator cannot equal 0. So note that the domain of a quotient, that's when we're dividing two numbers together, does not include x values for which g of x, that's the denominator, equals 0. So let's try this. I'm going to first jump down here to letter B. B is a teeny bit easier. Let's take a look at this f function, 6x to the 1/3 power. We know that 6x to the 1/3 power, another way to write that is 6 times the cubed root of x. Well, the cubed root of x, you can plug in any number for x. Positive, the cubed root of 8 is 2, or negative, the cubed root of negative 27 is negative 3. You can do positives and negatives. You can even do 0. The cubed root of 0 is 0. So the domain of this is actually all real numbers. Now this parent function is also a cubed root. Look at the denominator. The denominator of our exponent is odd. Odd is great. Odd, you can do positives and negatives inside that radical. When that is a 3, your index is a 3. They match. The 1 is just how many of these that we have. We discussed that on the simplifying expressions. So when we go down here to add them together, not much is going to happen. The only way you can add two expressions together is if they're like terms. You could put them in radical form, you could keep them in exponential form. This would be 8x to the 1/3. Your domain for this, because the parents are all real numbers, this domain is all real numbers. And the result also gives you the cubed root, which is all real numbers. The domain for f plus g is going to be all real numbers also. And we're going to see the same thing occur when we subtract. That gives us 4x to the 1/3. Because the parents were all real numbers, that means every number is available. And then when we look at the result, we still have all real numbers, so nothing is eliminated. So even when you subtract, our new domain is still going to be all real numbers for this type of example. Let's look up here. When we look at the parent function, this f of x, x to the 1/2 power, what type of radical is that? That's a square root, 3 square root of x. And this is minus 5 cube root of x. So the cube root we said was all real numbers. But the square root, of course, we cannot use negatives. So the domain here, the domain would just be x is greater than or equal to 0. It cannot include negative numbers. And the same thing for this side. So the only numbers that we can consider, even when we put these two functions together, is greater than or equal to 0. Negatives cannot be plugged in because it doesn't work for both sides. So when we add these two functions together, there's our f function plus the g function That plus doesn't change the game too much, so it's just add our like terms. So we get negative 2x to the 1/2 minus 3x to the 1/3. The 1/2 means a square root. We're limited on what our domain can be. The 1/3 is a cubed root, and that we are not limited. But because we are limited here, our domain for when we add this f function and g function together in this case is going to be what the parents were, greater than or equal to 0. Even when we subtract them. Minus this function. So here we got to be careful to distribute that correctly. So we have 3x to the half minus 5x to the 1/3 plus 5x to the half minus 2x to the 1/3. We collect our like terms, so halves go together. We have 8x to the half power minus 7x to the third power. There's no way to group that closer together. And again, our domain, even in this case, all real numbers for this one, just the values that are non-negative for this portion. Therefore, where are they the same? Where you are non-negative. On our final page, we're looking at our f function and the g function. Well, the f function is 5x to the 3 halves. The g function is negative 2x to the 3 halves. Well, let's look up and see what these parent functions are. It's to the half. So here, for this problem, the half gives you an index of 2. Typically, we don't even write the 2. That's a square root of x to the third power. That's where the 3 would go, and that's where the 2 would go. Well, similarly over here, the 2 would go as your index. You could even put the 3 either on the outside of the square root, or you could even put it on the inside of the square root. It wouldn't matter. That's where the 3 goes, either on the outside or the inside. But the main thing that we're looking for is right here. This is even. If it's even, then our domain is going to be what? When the index is even, we can't have negative numbers in our in the square root specifically for this one. So our domain here is x values greater than or equal to 0. So when we subtract them, we're going to get 3x to the 3 halves. Again, that's a square root. So our domain has to be greater than or equal to 0. When we come on over to subtract them, nothing too creative happens. So we got 2 negatives, so that means we're going to add. That gives us 7x to the 3 halves. Again, the denominator is even. So that requires all real numbers. Well, almost said that wrong. It includes the non-negative numbers, so 0 and bigger. Well, since that was the same thing as the parent, it fits together really well. No surprises. Down here, when we look at to the 2/5, so 6, the 5 is your index, and the 2 is the power on the x. Same thing over here. Since the 5 is an odd number, like a 3 or a 5 or a 7, the domain is all real numbers. Because you can plug in positive numbers, you can plug in negative numbers. So your h of x, 6x to the 2/5, minus negative 8x to the 2/5. Because the exponents are exactly the same, we're allowed to add these together to get 14x to the 2/5. Same variable, same exponent. We can add those together. And our domain would be all real numbers. Well, now let's start looking at this and seeing what happens when we multiply or divide. That's where life is going to be different. Well, this is 7. This is essentially 7 times the square root of x. Our domain of this f is going to be x values greater than or equal to 0. This is the 6th root of x. Again, the domain is going to be x is greater than or equal to 0 because they're both even indexes. The denominator's even, so the index is going to be even. We don't typically write the 2. I wrote it earlier just to show you where it went, but we typically wouldn't write a 2 for a square root. So we're going to take 7x to the 1/2 times x to the 1/6. How could we multiply those together? To multiply these together, we have to add exponents. To add exponents for fractions, we have to get common denominators. So this is 7x to the 4/6, and really that's the way we should leave it, and we'd be totally okay. But that can be reduced down to an exponent of 2/3. Well, it looks like this is an odd denominator, which would mean all real numbers. But you have to look up at the parent function, see how this was made, and recognize that we were only able to use non-negatives to begin with. So there's no way we can use all real numbers now. So it's a little bit better if you look up here at the 4/6. That's an even. So yes, our domain for multiplying is going to be greater than or equal to 0. Even though we have a denominator of an odd, of a 3, because it could only include positive numbers, non-negative actually, non-negatives, we cannot include the negatives that this would allow. Let's look here. 7x to the 1/2 and x to the 1/6. How do we go about simplifying that? We're going to take 7x to the 1/2 minus 1/6. So again, we got to get common denominators. So that becomes 2/6, which can reduce down to 1/3. Again, it looks like it's 1/3. It looks like the cubed root of x. But because this graph, this equation, was made, this expression was made from these two parents, that they were both having domains non-negative, we cannot include any of the negatives. But looking at the format of the question, there's also an additional requirement. What situation do we have to worry about? When there's an expression in the denominator, we have to watch when that becomes 0. So we can't be negative because of the parents. We can't be 0 because of the way that this is formed. So our f divided by g, in this case, is going to be x values that are greater than 0. It cannot be 0 because of the question. It cannot be negative because of the parents. So we'll take our 4x and our x to the 1/5. Well, what's your domain for 4x? The domain for an odd is going to be all real numbers. And here, since the denominator is odd, the domain is going to be, the fifth root can deal with negative numbers, so it's all real numbers. So in this case, 1 plus 1/5, 5/5 plus 1/5 leaves us with 6/5. So look at that denominator. Not much a surprise, nothing really changed on us. So if nothing's changing, when we're multiplying these two functions together, that means we're going to add the exponents. We're going to be able to keep the domain that the parents had and what this has all in common. So it's all real numbers. Let's look at what happens here with f and g. So this is 4x to the first minus 1/5. So 5/5 minus 1/5. We're trying to work at subtracting the exponents. So we got x to the 4/5. Well, what would our domain be for that? The parent function started out with all real numbers. When we worked through the problem, we still had all real numbers. But don't forget, this denominator doesn't allow the denominator to be 0. The only thing that makes this 0 is 0 itself. So it's all real numbers except x equals 0. Okay, you go ahead and try these. You can pause the video, try them out, and then turn it back on and see how you did. So we take our f function and the g function. The f function is a parabola, so the domain is all real numbers. A square root, so the domain is x is greater than or equal to 0, so non-negatives. We're going to multiply the two together. So when you multiply x's, you're going to add exponents. So we're down here with 2x to the 5 halves. The 5 halves tells us that this is a square root type problem. Now let's look at the parent function. Every number is available. Here, just the numbers greater than or equal to 0 are available. So when we put it together, that makes it look like greater than or equal to 0. That would be our domain. So f times g in this situation is going to be greater than or equal to 0. And when we divide them, 2x squared over x to the half, that means that we are going to subtract exponents. So when we divide, our new domain is going to be, the parent function was all real numbers and non-negatives. The result kind of gives you non-negative, so it's looking like that. So 0 or bigger. But look that this is a fraction. We can't have anything in the denominator that's going to make it 0. So we've got to watch out for that also. So we're just looking for all positive real numbers.